Hi, I'd like to introduce Mark Callaghan, who worked on improving MySQL for web-scale deployments at Facebook and Google for over a decade, and currently works at Facebook on RocksDB, MyRocks, and MongoRocks. Prior to this, he spent several years at Oracle and Informix, working on RDBMS internals. So, without further ado, I present Mark on read, write, and space efficiency.
So I'm a software engineer at Facebook, and in theory, that means I get to write software. But my job has evolved, so I mostly read and debug open source databases. And I've been fortunate to spend a lot of time in the MySQL and MongoDB communities and help make open source databases better, and also meet a lot of smart and talented people working for the companies behind these products. I'm here to speak today about the relationship between performance and efficiency for databases. I think there's too much focus about, or we spend too much time speaking or talking about performance and isolation, when really the relationship between performance and efficiency is the interesting thing for me. My focus is transaction processing. So I claim that I do small data, not big data. The database tier is still large in aggregate, but the transactions are short running. So there's a lot of marketing for open and closed source databases. And frequently, the motivation for the marketing is performance results. So marketing teams love benchmark results that motivate press releases, claiming one product is better than another because we get more throughput or we get a lower response time. But in reality, there are many aspects to defining what makes a product better beyond performance. For me, efficiency is a big deal. A more efficient database lets us handle next year's workload growth on the hardware that was acquired the previous year. Manageability makes database operations team happy when the on-call is able to sleep at night despite the various failures that are guaranteed to happen when you're running on enough machines. Usability makes developers happy who don't waste time re-implementing features that you really want to see in the database engine. Availability makes the end users happy when your database-backed web scale service is reliable. So I'm not claiming that any of these is more important than the other. It's just my focus is performance and efficiency. My goal is to share, well, hopefully convince some of you that really we should be shifting the discussion to efficiency. For a lot of us, I think the requirement is good enough performance, at which point we can focus on efficiency. And the reason is we don't have an infinite demand for throughput, nor do we benefit from zero-second response time. So there's some point at which improvements in performance don't affect the end user experience. Improvements in efficiency almost always have a benefit. You can either put more features onto your service that's database backed, or you can use less hardware. You can be more effective. So really, I still talk about performance, but I want to optimize for efficiency. So I've been doing databases for about 20 years. The first half of my career was at Informix and then Oracle. And so that was about 10 years. I never saw a production database deployment. I never got close to a production database deployment. I did very interesting work. I learned a lot, but not being near databases that are being used makes it hard to do work that's relevant. So my suggestion is anyone doing research or development for databases, spend some time, spend a sabbatical or an internship, but spend some time near production. For the last 11 years, I've been too close to production database deployments. So in 2005, I joined Google. At the time, Google told you what your project was. You didn't get to choose. And I was working with the smartest, most productive person I've ever met on a small project. So at Google, that meant I would be ranked number 2 on the team 4 times per year because this person was that talented. I did not want that to happen, so we were running MySQL within ads for a critical use case. We had modified MySQL, but nobody wanted to touch the code anymore. So that was my barrier to entry. I started working on MySQL. There was a lot of low-hanging fruit. Multi-core performance was not really there at the time. Reliability, crash recovery in the replication code was weak. Monitoring didn't really exist in the code base. So it was a great opportunity to do interesting work and make the product much better. About 7 years ago, I joined Facebook and inherited a much larger sharded MySQL cluster that needed to be made better. At the time, we were using InnoDB without compression. The InnoDB team had implemented compression, but it only was performant for read mostly workloads. The workload that we had a lot of writes, and so we spent some time fixing InnoDB compression to make it performant for read-write, and then deployed it. That shrank the amount of storage we needed in half. Since then, the tier has grown to the point where we have multiple copies or multiple replicas in production. It's many tens of petabytes, despite the 2x compression. We want additional compression. We'd like to have half of the many tens of petabytes. The database tier is using SSD, so there's a lot of motivation to use less SSD. We don't think it's possible to get more compression from InnoDB, so we have been working on a MySQL storage engine for RocksDB. It is going into production this year. We are expecting an additional factor of 2 in compression. So we expect to compress by a factor of 4 versus the uncompressed size. This is a very big deal given the size of the storage tier. So as part of this, I actually spent some time evaluating open source database engines. And we had a lot of conversations within the company about, oh, look at this database. It looks better. And even now, conversations pop up at work. Hey, someone published a result. We should look at this other open source database engine. And so the question is, how do we improve the quality of these discussions within work so that we're not just talking about performance? And from that came really a framework for discussing efficiency and performance, along with a lot of discussions I've had with academics. And so eventually a paper was published. I am last author on the paper. Several people from Harvard are the first authors. It was published this year. They are doing a tutorial at SIGMOD this year. The title is the RUM conjecture. RUM stands for read, update, modify. The idea is that between, I was using a different terminology, read, write, and space amplification. Instead of amplification, we can think about efficiency. Of these three, of read, write, and space efficiency, you can't optimize for all three at the same time with one algorithm. You get at most two. So you trade. You can get more read efficiency by sacrificing write or space. This is a conjecture. It's an assertion. There is no proof today. Perhaps there will be a proof. But for now, it's common sense or motivated by experience. So the Rum conjecture talks about amplification. What do I mean by amplification? So for space amplification, it's the ratio, the size of the database files versus the size of the data in the database. It's a number, could be less than or greater than 1. In the paper, they claim it's always greater than 1. It's not clear how we account for compression. Read and write amplification is just the amount of work done per database request. And I'll define that in the slides that follow. So what do I mean by work? It depends on whether we're talking about storage or CPU. And for storage, the metrics we use for work depend a lot on whether we're talking about a disk array or an SSD. The disk arrays tend to saturate first on random operations for transaction processing. If we're using an SSD, we're more likely to saturate on bytes transferred. But we also have to account for the CPU overhead for different database algorithms. And so the metrics there can also be considered in the work done. So if we're using SSD, we're likely to use compression. If we're using compression, every time we read a block from storage, we need to decompress it. If we're fortunate enough next year to be using the fancy 3D crosspoint device named Optane from Intel, which is claiming a 10 microsecond read latency, you don't want to spend 100 or 200 microseconds decompressing after that 10 microsecond read. You might as well be using a NAND flash at that point. Other metrics for CPU overheads, how many bytes are we moving, either reading or writing? How many data structure searches are we doing? And finally, the simplest one is just what's the CPU latency or overhead per request? So I said the amplification is work done per operation. From the definition in the paper, I would use the basic database operations exposed by the RocksDB API. We have a point read or a range read. The range reads that I see in production tend to be short, maybe a few thousand rows at the most, except for when we're doing logical backup. Then the other operations are put or write and delete. And if we think about processing SQL, which is at a slightly higher level, the typical work done for an SQL update is either a point or a range read, followed by a delete for the old value of the row, and then we're doing a put for the new value of the row. If there are secondary indexes that have to be maintained, then we would be doing multiple puts internally for an SQL update statement. In some cases, we can optimize it either by skipping the delete or even skipping the read and the delete. So the real point here is that we have these low-level basic operations from which the statements we might use in SQL are using a combination of them. So in the end, we might construct, with lots of hand-waving, performance models for read, write, and space amplification. And we might assign numerical values to each of these, and we can even measure them. Now, on their own, they're not very interesting in isolation. If I said, well, the space amplification is 10 or 12, that's not that interesting. The use for them is to compare different database algorithms, to compare a B tree and a log structured merge tree, which I've spent a lot of time doing at work. And just these are estimates from one of the workloads that I've measured. If we look, the read performance is frequently similar between B trees and log structured merge trees that I've been testing. The real difference is on the write and the space efficiency. And so for one example, I was seeing about 10x or even 20x less write amplification with a log structured merge tree and 2x less space amplification. So 2x less space amplification means I use half the space. 10x less write amplification means SSD endurance is less of an issue. Now the problem with using numbers like this is that there's a lot of context which is not always explained. Context in which these numbers hold. And the context is the workload and the hardware. You know, the hardware, how much data fits in cache? What's my cache hit rate? A lot of assumptions that make it hard to have universal statements or claims of efficiency. Now I said that one algorithm would not be optimal for read, write, and space efficiency. What do I mean by that? If I look at the set of useful database algorithms, something I would actually consider using in production, in practice, one algorithm is not going to have lower values for each of these compared to another algorithm. So you know, a log structured merge tree is likely to win on write and space efficiency versus the B tree. The B tree wins on read efficiency. So we have to focus on the efficiency metrics that we care about. Now, read efficiency, read amplification is read, write, and space amplification all have a lot of factors that we need to consider. For read amplification, am I doing point or range queries? There are optimizations for point queries with some algorithms that don't extend to range queries. Bloom filter is an obvious one. With a log structured merge tree that depend on Bloom filters for making point queries efficient, generally you don't get to use that for range. Are we looking at random operations or byte transferred for storage? Disk arrays saturate on random operations first. SSD will saturate on bytes transferred. Are we looking at CPU or storage overheads? And then finally, the cache effect, which makes it really hard to reason about algorithm efficiency without context on the workload and the hardware. For write amplification, really the first thing is the difference between the ingest and the total write rate. So the ingest is the rate at which I'm pushing bytes into the database engine. And if I'm using something like a log structured merge tree, this is easy to measure because any change, insert, update, or delete, becomes a put in the API. And so I can count the bytes at which I'm writing into the database. But even for a B tree, I can just look at the write at which the redo log is written. And that would be the ingest. The total write rate is what happens in the background to persist database changes. With a log structured merge tree, I'm doing compaction. With the B tree, eventually something is flushing dirty pages back to disk. And so I can count the page writes for a B tree. I can count the bytes written from compaction. Again, CPU versus storage. Depending on my workload, I might be bottlenecked on one. If I'm using a very expensive compression algorithm, then the latency, the speed at which I can compress pages will determine the speed at which I can persist the database. I also need to consider the work done in the foreground versus the work done in the background. In a well-tuned B tree, the background work, writing back dirty pages, doesn't get in the way of user queries. Unfortunately, if I can't flush dirty pages fast enough, then I will block page reads that need a clean page from the buffer pool. Same thing with compaction in a log structured merge tree. If compaction doesn't happen fast enough, eventually I need to throttle the ingest. Space amplification, the context here is I need to be clear on the difference between the memory and the persistent or disk or SSD overheads. In some cases I have the choice between causing fragmentation in memory versus causing fragmentation on disk. If I'm using compression, do I want my compressed page size on disk to not have fragmentation? So do I want to minimize padding there, or do I want to minimize padding after I decompress the pages? I talked about space amplification being the ratio for the size of the database files versus the size of the data. How do I measure the size of the data? Am I including the benefit of compression in that? And am I including the size of secondary indexes? So in the end, with all this talk about amplification, what I end up using for my evaluation is hardware efficiency metrics. The problem is that for amplification, it's very hard to isolate hardware utilization per put versus per get versus per range scan. So what I do is just measure the throughput in terms of queries or transactions per second. And then I measure hardware utilization. For IO stat, I get reads and writes per second, reads in kilobytes, read and written per second. From VM stat, I get the CPU utilization. And then I normalize the database throughput by the hardware utilization. So I can compute how much CPU do I use per transaction? How many disk reads do I use per transaction? One caveat, if you're using IO stat and you're using SSD and discard is enabled, trim, the bytes trimmed, are counted as bytes written. So with RocksDB, in steady state, IO stat will overstate by a factor of 2 the rate at which you're really writing to the SSD. Fortunately, we have Linux kernel people at Facebook who hopefully will give us counters that will let us accurately measure bytes written for SSD. The numbers here are from an open source benchmark called LinkBench, which is a social graph transaction processing benchmark modeled on what we do at Facebook for the user database tier. Both cases, this is using MyRocks, which is a RocksDB storage engine for MySQL, and InnoDB. I'm getting about 5x the throughput on MyRocks. Hey, great, better performance. So normally I would just publish that number, nice bar chart, and then be done. However, I want to show the relationship between efficiency and performance and try to explain this result. And the reason we're getting more throughput is we're using less hardware per transaction. InnoDB is doing almost twice the number of disk reads per transaction. It's writing about 20 times as much to storage per transaction, which is a big deal if SSD endurance is a concern. InnoDB was using about twice as much CPU per transaction, and even with compression, the database on disk was almost twice as large. So across the board, MyRocks is more efficient. It gets more throughput. These workloads tend to be I/O heavy so that we don't expect the database working set to fit in memory. We have SSD. We're willing to use SSD as long as there's not too many reads per transaction. We can still satisfy the response time goals. And so more effective use of I/O means we get more throughput. So I wanted to talk about the trade-offs we make between read, write, and space efficiency. Now, indexes improve read efficiency. You read less data when you have a good index. Wider indexes that make your indexes covering for queries means you're going to do less random I/O for queries that require more columns. Indexes also allow you to cluster data to make range scans efficient, but this comes at a cost. Indexes increase the size of the database, so you reduce space efficiency. Indexes require maintenance, so you reduce write efficiency. We make writes more efficient with a log-structured approach, where we're using mostly sequential I/O to persist writes. Now that comes at a cost in read efficiency, because we have to read or search more locations for data for queries. Space efficiency. If we're using a write-optimized algorithm, the more frequently that we run garbage collection, the less garbage we have in the database, the less wasted space. But garbage collection implies writing, so you sacrifice write efficiency to improve space. If we have a B tree, we're running defragmentation. And defragmentation reclaims space at the cost of doing more writes. And then finally, compression. Use less space. You make reads more expensive because they must decompress after reading from storage. This graph here is a common thing you will see with an SSD or with a write-optimized database. There's an inverse relationship between space and write efficiency. The less over-provisioning we do, the less wasted space improves space efficiency. So if we're using 90% of the space on a storage device, space amplification is about 1.1. However, at that point, assuming a uniform distribution of writes, write amplification will be about 10. If we increase space amplification, so we're only using half of the storage device, we can reduce write amplification to about 2. So SSDs do this via over-provisioning. Write-optimized database engines do this just by tolerating more dead data. Another example of efficiency trade-offs that we make for the social graph transaction processing workload, and this is the workload for which many tens of petabytes are used. The most common query is a range scan. So we have an equality predicate on 2 columns, ID1 and L type, a range predicate on the timestamp column. We need to order the results, and we have a limit clause. So we have really 3 choices for the index. When I joined Facebook, we had choice number 2. So we had an index really on 3 columns to cover the equality predicates and the range scan. That meant that the columns that had to be retrieved for the query were not in the index. Here I'm showing a limit clause, limit 1,000. In production, the query frequently had limit 10,000, which meant in the worst case, we were doing 10,000 random disk reads for this query. If the database cache was cold, it was lousy for response time. We wanted to get from index solution number 2 to index solution number 3. We wanted to make the index covering for this query. Doing this without downtime required us to implement a framework for doing online schema change that we called Online Schema Change, OSC. And it is one of the most popular tools within Facebook. We are incrementally trickling schema changes for a variety of tables across the tier, 24 hours a day. We don't do the schema change on all replicas at the same point in time. It iterates slowly through the tier. I didn't predict it would be this popular a tool at Facebook, but we actually also use it to defragment some tables in production. We'll just do a schema change to rebuild the index. It's non-blocking. It doesn't interfere with response time for users. It doesn't prevent writes when it's in progress. So it's been a very effective tool. However, making the index covering essentially doubles the size of the table. And this might be 1/3 of the database tier in size. We've doubled the size of that table, trading space efficiency for read efficiency. The open question, I think, that I hope is interesting to academics is, for different database algorithms, how do we talk about the trade-offs, the deltas between read, write, and space efficiency? For some algorithms, the trade is more expensive than for others. So I wanted to talk about some of the database algorithms or file structures, database structures that I spend time evaluating. I'm not going to try to explain each of them. I think that's too much detail. But also, as a user of databases, I care more about performance characteristics or performance behavior and efficiency behavior, and not so much about the algorithm itself. But really, for a few years, I've spent a lot of time looking at B trees with InnoDB, WireTiger, which is a relatively new copy on write B tree, which is now part of MongoDB. ForcedDB is a log-structured database engine. And then I've spent a lot of time on RocksDB, which is derived from LevelDB. It's a log-structured merge tree. I spent less time with Cassandra and HBase. While I claimed I wouldn't talk about implementation, I just have one slide on ForcedDB because I think it's new enough and unique enough that it's worth covering in one slide. Log structured, so when rows are persisted to the database, they're just written to a log once. The index structure is separate from the row log. In this case, the index structure is a copy on write trie. However, this approach could use other solutions or other technology for the index structure. The rows eventually require the log eventually requires garbage collection. There's something scanning previously written log segments, looking the rows up in the index to figure out if that is the live version for the row, copying it to a new segment, otherwise it's dropping it. So this is implemented by ForcedDB. It's now part of Couchbase. So I think there will be production quality version of it. But really my focus is on behavior, performance and efficiency. And there's some questions that I try to keep in mind when talking about efficiency and performance. And the first is, what do reads search? How many data structures have to be checked on a point or a range read? The next is that when I'm persisting changes to the database, do I have to write back pages, or am I only initially writing back the row? What are the bounds that I can expect for space amplification? Is the primary key index clustered? Is the index support, is it always efficient for range scans, or is there an option for an index that is only good for point reads? And then what data do I need to have in cache for this to be effective? So the first one is, what do I have to search for reads? And really, if I just had one bit of information in this case, I would say, is the engine or the algorithm search one versus search many? And so a B tree is the example where I would describe it as search one. I have to search one data structure for a point read. And so if we look at the pyramid on the right, If I have a tree with 4 million keys, I'm doing about 22 key comparisons for this search one structure. If I have a differential structure, so I have a sequence of trees to search, going from a small tree with 16K entries to a slightly larger tree with 256K entries, and then finally the tree with 4 million entries, I might have to do 54 key comparisons to search all three. So I'm doing significantly more work, whether that's CPU or I/O bound. I'm just doing more work for a search many structure. And I don't always want to get lost in the details of how much work I have to do, so I'll just say one structure is search one, the other is search many. The next question is, how do I persist changes to the database? With the B tree, I'm writing back pages. In the worst case, I write back a page per row change. Or if I have multiple indexes, I might write back multiple pages per row change. A page is much larger than a row, so this is a source of write amplification. For a write-optimized database algorithm, initially I'm only writing back the row to some kind of log. However, there's usually some kind of garbage collection that happens in the background. So we need to think about when is garbage collection needed. In the log structured approach used by RocksDB, the reason for garbage collection is to remove dead versions of data. If you have an insert-only workload so that you're never making any rows dead, in theory, you never need garbage collection. And you might have a write once solution, which is great. For a log-structured merge tree, garbage collection is also used to remove dead versions. We call garbage collection compaction, but garbage collection is also used to cluster keys. So you're potentially rewriting previously written data, which is another source of write amplification. Is the primary key clustered? It is an interesting question. Most of my web scale experience is with InnoDB and now RocksDB, and in both cases the primary key is clustered. So this has advantages and disadvantages. First, the primary key index is covering for any query that's doing a primary key lookup. So once you reach the leaf node for the tree, you don't have to do any additional I/O. With a B tree, compression is much easier if you have a clustered primary key. If the in-memory copy of a leaf node is too large after compression, you do a page split. So this has made compression performant for transaction processing with InnoDB. The potential problem is that the secondary index references the primary key index. So if you're doing a secondary index search and you don't have all the columns that you need, you then have to do an additional tree search on the primary key index. So you can spend more CPU in this kind of setup. Okay, so support for range scans. In most of the open source database engines, the indexes always are efficient for range scans, which is great if you need range scans. It's not so great if you don't. There's a cost to order data in the index, and that cost is when you write a new value for a key, you need to co-locate it with logically adjacent values of the keys, meaning you're rewriting previously written data, more write amplification. We don't have great support for hash indexes in the open source databases I deal with. In theory, if we did, we could reduce write amplification. Another question is what data needs to be in cache? So for me, it's easy to reason about worst case performance. If you think about what data should be in cache, so you do at most one disk read for a query. For a covering B tree index, I need everything but the leaf nodes in cache. So then I do one disk read to read the leaf node on a query. If I don't have a covering index, then after I reach the leaf node, I need to do an additional search of either a table space file or another index. And so I assume for the non-covering index, that has to be fully in cache. And then I'll spend a disk read going from that leaf index, a leaf node, to something else. So in the case where I have a covering index, in cache, I need a pointer and a key for every leaf node in the index. If the leaf node is 8 kilobytes and that pointer is 32 or 64 bytes, I don't need much data in cache for a large database. If the index is not covering, now in cache, I need a pointer and a key for every index entry, for every row in the index, which is a much larger requirement or overhead for the cache. So when we focus on read efficiency, we really want covering indexes, which allows us to have a much larger database to cache ratio. So in the end, I think about a geek code. How efficiently can I describe database algorithms? And here I'm really comparing InnoDB as the B tree, RocksDB as the log structured merge tree, ForestDB as an implementation of a log structured database, and the generic log structured database engine. The B tree and ForestDB are search 1. RocksDB is not, so RocksDB suffers on the write efficiency side. RocksDB and ForestDB are write row for the data. They tend to benefit on the write efficiency side. When compiling this, it became clear to me that there still are algorithms that I guess I'm still waiting for. Really, if we think about opportunities that exist, I think there will be a few more variants in the log structured database engine family. If we get a hash index that's efficient for point queries, we can reduce write amplification. And we will be able to run some workloads much more effectively. There's also still pending optimizations for databases dealing with large objects, write once workloads, and there's a lot of innovation waiting still or in progress for time series workloads. So in the end, which file structure is better? So I have two claims. One, it depends on your workload and your context. And the second one is, I'm in the RocksDB camp. I work on it, so clearly, either via MongoDB or MySQL or via pure RocksDB, consider using it. I'm not listing here, we have many other companies that are currently running RocksDB in production. We have a storage engine for MongoDB that's running in production. Later this year, the storage engine for MySQL will be running in production. But it really comes down to what do you care about? Are you looking at throughput? Are you looking at efficiency or response time? Do you need compression? Are you doing range reads or more point reads? Is your workload I/O bound or is it fully in memory? Do you care about write amplification? Are you using SSD and does endurance matter? If you're using SSD in the cloud via another vendor, endurance might not be your problem. It might be the vendor's problem. But if you're purchasing the SSD, then you need to think about endurance. And then is your workload read or write heavy or mixed? So my short ad for RocksDB, I work on RocksDB. It's an embedded key value engine derived from LevelDB, but it's very different at this point in time. We have storage engines for MySQL called MyRocks and for MongoDB called MongoRocks. MongoRocks is in production. MyRocks later this year in production. We have the opportunity for trade-offs between read, write, and space efficiency. with RocksDB. We have two styles for compaction. Leveled compaction minimizes space amplification. Universal compaction minimizes write amplification. We have tuning for compression. We can use Snappy, we can use zlib. Later this year, we will be using zstandard. We can vary the structure of the tree to also alternate between read and write optimizations. The big reason for moving from InnoDB to MyRocks is 2x better compression, meaning we use less storage, and 20 times less write amplification, meaning endurance is less of an issue. These were measured both from production workloads and from synthetic benchmarks. Compressed and uncompressed InnoDB were at least 2x better. For write amplification, we are writing about 20x, for one of the workloads, 20x less data to storage per transaction. I was trying to come up with workloads for which RocksDB beat and then lost to InnoDB. The workload I chose ended up winning in both cases, but the real purpose is just to show the methodology I use for reporting performance and efficiency. So really, I'm listing throughput and then hardware utilization. So in the first case, an insert-only workload, not a surprise that MyRocks wins. It is a write-optimized database engine. Secondary index maintenance for non-unique indexes does not require disk reads or reads of the old value of the index entry. So we have less CPU and storage overhead. The interesting thing is that it was more effective on all of the metrics. So fewer disk reads, less data written, lower CPU utilization, better compression, whether it was compared to compressed or uncompressed InnoDB. In the first case, the database is much larger than RAM. I've repeated the test for a database that was fit in cache. In that case, the insert rate was now comparable between InnoDB and MyRocks. Hardware efficiency metrics tended to still be better for MyRocks. So then I added queries to the mix. In this case, I limited the insert rate to a very small value, and then tried to see how fast I could run queries. In the first case, the IO-bound case, I'm getting significantly more queries per second from MyRocks. I'm doing fewer disk reads per query, which explains the better QPS. I'm using less CPU per query. The database is smaller. It has a better cache hit rate. Repeated the test for a database that fits in cache. In this case, I get slightly better QPS from InnoDB, lower CPU overhead from InnoDB. The database still was smaller with MyRocks. My point here, the purpose for showing this is, of course, I'm proud of the results we get from MyRocks, but it's to motivate the methodology. Focus on performance and efficiency together. So really, if there's one slide to hopefully that you take away from my talk, there's no free lunch. We tend not to get better read, write, and space efficiency. We tend to trade one for another. So if you're looking at performance results, try to keep in mind that you really need to see an explanation of them. Why is one thing faster than the other? And hopefully get to see hardware efficiency metrics to explain the difference in performance. If you're looking at performance, always performance and efficiency. And then the last point, really, if you get the chance, spend some time near a production database deployment. If you're building a product or you're doing research in academia, it will greatly inform your research. We have a landing page for RocksDB. This is also the pending landing page for MyRocks and MongoRocks. So we also have groups on Facebook. We have email lists. We're very happy to hear about other people using the technology. So please join the community. Thank you.
So I have a very basic question. What do you do when the data doesn't compress?
So with InnoDB compression, we have in-memory pages that might have a fixed size. Let's say the fixed size is 16K, and the on-disk page also has a fixed size, either 8K or 4K. So we're assuming the in-memory page shrinks by a factor of 2 or 4. When it doesn't, we do a page split of the in-memory page, and then the split pages will compress to that fixed size. The problem with InnoDB, and it's something that we ended up doing some clever work to make better, is that over time you might have a data set that doesn't compress by 2x. It might compress from 16K to 10K on a consistent basis. And you need it to shrink to 8K. So the solution is to only put more padding in the page and only use, let's say, 14K of the in-memory page so that it's more likely to shrink to 8K. And we added code to InnoDB to detect when this was required and to dynamically increase the padding for in-memory pages. With RocksDB, it doesn't matter. The in-memory blocks are just compressed, and we just write out whatever it compresses to. So there's no alignment from the in-memory page to the on-disk page. When we do a page read from disk with RocksDB, there's no alignment. So the page can start at anywhere, any byte offset, and can end at any byte offset. So if it doesn't compress, the real question is, what does the compression algorithm do if we give it data that doesn't compress? And we don't think much about it.
But don't you need to size the underlying storage for the worst case then? So you don't actually get any space savings, or you could get in a situation where you fail, right?
Yeah, so in the sharded database where you're explicitly putting some data on some nodes and some data on other nodes, you really want to avoid it would be great if you could use 99% of the allocated space, but you're putting many shards on a node. We have a tool for doing online migration of a shard between nodes, so we can move data without downtime. And if a node gets, let's say, more than 90% of the 90% full, then we would move some shards off of it to leave this room for growth.
Okay.
So we never have the bin packing problem. We never try to say there's only one shard on a server. We try to put at least 4 or more to make the bin packing easier.
So you basically assume it doesn't happen with all at the same time, so you have enough underlying specs. So otherwise, the compression would only help you with the bandwidth, but not with the actual storage, right?
We've had shards get full,
Yeah.
but these shards tend to be we have this user tier where the workload on every shard is similar. And then we have these special tiers where someone needs a database instance and we give it to them on a special tier. And they only run on one or a few shards. Some of those shards have unpredictable growth, and some of those shards get full. But the user tiers, they're much more predictable.
Thank you.
Intuitively, you would think that if you were to optimize for space on disk, that you'd actually get improvements in both read and write performance. Traditionally, databases have optimized only on how little I/O they can do or how they can optimize data locality. So you'd think if you have to read less data or write less data, you could perform better. And maybe if you think about other on-disk formats like column stores, you can use simpler types of compression that are less CPU intensive. You can use Huffman coding for low cardinality columns. You could use run length encoding if most of the values are similar. Have you thought about, because these are really like MySQL's a row store. Have you thought about whether this would work for the types of workloads you're looking at?
So we have the author of Z Standard, I might mispronounce his name, Jan Collette, giving us a lower CPU variant of zlib-like compression. We have someone on the RocksDB team looking at some of the compression techniques you're talking about, but it would really be, it might be the PAX approach where you have column-wise within a page, because we still don't want to do, if we have 10 columns, we don't want to do 10 page reads in the worst case, because we need to preserve I/O capacity. Even with SSD, we still want to preserve I/O capacity. So we are looking at things beyond block compression, but column store, if the column store still means that we're using a lot of disk, then the column store is unlikely to work if it amplifies the worst case read IOPS we have to do. For this workload, it's transaction processing 1 to 10,000 rows per query. If we see a long-running query, it's a bug in production on some of these database tiers. We just don't, except for logical backup. Logical backup is the only long-running query we tolerate in that workload.
How does providing support for various isolation levels factor into some of the trade-offs you've made on the DB, or is that handled by a higher level, like a higher layer in MySQL, and largely it's not a concern?
So we had an interesting discussion when implementing RocksDB for MySQL about isolation, because InnoDB has gap locking for repeatable read. And it's not really repeatable read because of the gap locking semantics, but it's a useful behavior that's provided. For MyRocks, I didn't want the team to implement the code to do gap locking. So we ended up providing Postgres style semantics for repeatable read, and then we also do read committed. And then we've probably been working more than a year to identify applications that depended on gap locking with InnoDB and have them fix their application, not depend on that feature. But if you're talking about isolation across nodes, we're sharded, so we only care about per shard isolation. We ended up implementing this transaction API for RocksDB. So MySQL uses it, but you can also use it directly with RocksDB to get repeatable read or to get read committed on top of the key value API. But I'm not sure if that's what you meant by isolation.
I meant more in terms of like, does it affect the trade-offs in terms of data structure, or is that not?
The real issue we saw was just the CPU overhead for repeatable read. But the person who implemented the feature ended up fixing most of the problems we saw. We tend not to have, so write transactions tend not to modify too many rows. So the implementation has a lock table to do the locking we require for repeatable read. That lock table tends not to get too big. And it has to fit in memory. So we won't allow a transaction to hold too many locks because we don't want to in MySQL, I think if you use RocksDB directly, you can run RocksDB out of memory just by trying to get too many locks. But for short-running transactions, it's not a big deal.
I think some of the metrics and comparisons you make do apply to more analytical workloads and more analytical style databases. Just a comment. Just wonder if you could speak a little bit to that. I know you're looking at OLTP style databases, but I think most of what you're talking about should apply to analytical workloads as well.
I agree. At Facebook, Presto is our big our new big data project, parallel query engine. And there's been some what I call bench marketing. So using performance to motivate claims that you're better than the other. I've seen it in both directions, comparisons between Presto and Impala, where both sides claimed better performance. And so certainly, I hope they focus in their marketing on more aspects of manageability, availability, efficiency, and performance. But I just, in production, I'd never get near big data. I'm always on the transaction processing side.
Cool. So let's
It's done?
take it offline. Yeah.
Okay.
So lunch is on the 3rd floor, and we'll reconvene at 1:30.